Mr. Watson very kindly invited me to speak to this mathematics class, but what I want to talk about is not mathematics, but physics. I want to talk to you about neutrinos. Well, physics and math are reasonably close together, so I don't feel too guilty about that, talking about physics, and I hope you'll be interested. Please interrupt me with questions whenever you have them. Before I really talk about neutrinos, I think I should talk about something a little bit more general, just to put neutrinos in perspective. So I'd like to ask a question. Given what we know now, how do we understand the most basic forces in nature, and how do we understand the most fundamental constituents of matter? You'll see in just a little while how neutrinos enter into that. So let me begin by writing down what we think are the most fundamental forces in nature. There are 4 in number. Gravity, electromagnetism, the strong force, and the weak force. Now, gravity everybody knows about. If you throw something up in the air, it comes down. And the moon is held in a stable orbit around the Earth by gravity. Everybody knows this fact. We have a good old theory of gravity. It was invented by the great Isaac Newton, an English physicist and mathematician, about 300 years ago. Newton's theory of gravity still works pretty well, and for most practical purposes it's entirely sufficient. But we also have a better, more modern theory of gravity, and that's called general relativity. That was invented by Albert Einstein a little less than 100 years ago. General relativity involves some pretty formidable mathematics, but it's a very beautiful theory, and it's been tested quite severely by some very, very precise astronomical measurements. And the tests and the theory agree in excellent fashion up to now. So that's gravity. What about electromagnetism? It's the workhorse of everyday physics, chemistry, and biology, and almost all of our technology. You probably know that everything in ordinary matter, for example, this blackboard, this floor, the air you're breathing, is composed of atoms, and you probably know that an atom consists of a very small, compact, massive nucleus, which consists in turn of protons and neutrons. And this nucleus is surrounded by orbiting electrons. I'm sure you know this, even if you haven't studied physics. The force that holds the electrons in an atom is the electromagnetic force. The forces that are involved in the chemical reactions, the force that's involved in chemical reactions is the electromagnetic force. Almost all phenomena in atomic and molecular and solid-state physics are electromagnetic in nature. So the electromagnetic interaction, or the electromagnetic force, is ubiquitous. It's everywhere. It plays an important role in almost all of physical science. So now what about the strong interaction and the weak interaction? The strong force is the one that holds protons and neutrons together inside the nucleus. And as we'll see in a little while, The proton and the neutron are themselves not fundamental particles. They're made up of something even more fundamental called quarks. And the strong force is what binds the quarks together inside of a proton or a neutron. As the name implies, the strong force is very powerful, but it's also very short range, only about 10 to the minus 13 centimeters. And what about the weak interaction, or the weak force? As the name implies, it's kind of feeble, but it's not unimportant. It's very important. If it didn't exist, we wouldn't either. And what does it do? Well, it's responsible for the decays of unstable nuclei, most of the decays of unstable nuclei, and of elementary particles. But it's responsible for a lot of other things besides, and we'll see that in a while. So these are the fundamental interactions in nature as we understand them at present. Now, these three interactions, electromagnetic, strong, and weak, they form a separate category from the gravitational interaction. Why? Because these three have to be understood in terms of what's called quantum mechanics. What is quantum mechanics? Quantum mechanics is a theory that was developed in the 1920s. At the time, it was revolutionary. It's immensely successful in accounting for phenomena on the atomic and subatomic scale. And with the aid of quantum mechanics, it's been possible to understand the details of the electromagnetic, strong, and weak interactions on the microscopic, that is, on the atomic and subatomic scale. And in fact, even to build a theory which is unifying these three interactions. That unification of those three interactions, theoretically, had its birth in the 1960s. And that unification has, with minor exceptions, also been very successful. That's called the Standard Model. Maybe you've heard that phrase. So the Standard Model is the unification of these three. But up till now, it's been impossible to enlarge that unification to include gravity. Nobody has been able to extend the unification of the three interactions to go forward. Another way of putting that is to say that nobody has succeeded in reconciling quantum mechanics with general relativity. Not for lack of trying, for sure. That's one of the most fundamental problems, unsolved problems in modern physics. And a lot of people are struggling with it, but so far no success. Maybe you've heard of the phrase string theory. String theory is an attempt to reconcile quantum mechanics with general relativity. Okay, so that's a very quick and superficial summary of the four forces of nature as we understand them. Now, what about the fundamental constituents of matter? Well, they fall into two classes. First of all, the quarks. And then another group is called the leptons. So let's talk about the quarks. These are the fundamental constituents that make up strongly interacting particles like the proton and the neutron. And there are 6 quarks in number: the up quark, the down quark, the charm quark, the strange quark, the top quark, and the bottom quark. The names are kind of frivolous, they don't really mean anything, but you know, once you give something a name, it sticks, and that's what you have to use. And these quarks fall into 3 groups or families: the up and the down quark, are together in one family, the charm and the strange quark in another, and the top and the bottom quark in another. Why do they have these distinct families? It turns out that an up quark can transform into a down quark by means of a weak interaction, and vice versa. Similarly, charm and strange, similarly, top and bottom. That's why they're divided up into these three families. Sometimes we speak of them as generations, so there are three generations. Now, the up quark, the charm quark, and the top quark all have the same electric charge. 2/3 of the fundamental unit of charge, which we call E, that's the charge on the proton. So the proton has a charge plus E, and the electron, which is another familiar particle, has a charge of minus E. And in terms of those charges, the charge of the up, the charm, and the top are 2/3 of E. And the down, the strange, and the bottom are minus 1/3 E. A proton consists of two up quarks and a down quark. Let's check the charges. A proton has a charge of 1 unit of E. 2/3 plus 2/3 is 4/3, minus 1/3 is 1. And a neutron is a neutral particle. It's 2. That's a better one. Thank you. A neutron is 2 downs and an up. Minus 1/3, minus 1/3, plus 2/3 is 0. A neutron is neutral. Okay, quarks, relatively recent theoretical invention. People first began thinking about quarks in the 1960s, and originally the only ones that were considered were the up and the down and the strange. But in the 1970s, the charm quark and the bottom quark were discovered, and in the 1990s, the top quark was discovered. We don't believe that there are any more. We think that there are only 3 generations. Another thing we can say is that for every quark, there's an antiquark. An antiparticle is the same as a particle, except it has the opposite charge. So an anti-up quark will have a charge of minus 2/3 E instead of plus 2/3. So we also have 3 generations of antiquarks: U bar, D bar, C bar, S bar, and T bar, E bar. These quarks all have charges opposite to those. And we have evidence for the existence of antiquarks as well as quarks. The whole panoply of strong interactions can be explained, at least in principle, in terms of quarks and their interactions. And the evidence for the existence of quarks is massive and convincing. But nobody has ever observed a free quark, because always quarks are imprisoned inside particles like the proton and the neutron. Nobody has ever observed a quark to escape from a strongly interacting particle like a proton or a neutron. So the evidence then for the quarks, even though it's very convincing, is indirect. Okay. So those are 100 years of research on electrons, so we know its properties, its mass, its charge, its magnetic moment, and other things extremely precisely, Electrons are everywhere. Every atom has electrons. Every molecule has electrons. Solids have immense numbers of electrons. Liquids have an immense number of electrons. Electrons play an important role not only in physics but in chemistry and biology, and of course in our technology. Our electronic technology, the name means electrons. So they're everywhere, and they're very familiar. What's a muon? It's a heavy electron. It's a particle which is very similar to the electron, but it's 200 times heavier. It was discovered in 1937. And the tau lepton was discovered only in 1975. It's even heavier. It's about 3,400 times heavier than an electron. We know almost as much about the muon as we do about the electron. A little bit less for the tau, because the tau is kind of elusive and hard to measure. We know somewhat less about the tau. Our measurements are not so precise. These particles, the electron, the muon, and the tau, are, as I said, very similar. And they have both electromagnetic and weak interactions. So now let's talk about the neutrinos. That's the principal thing we want to talk about. The neutrinos, each neutrino, nu E and E, are closely related because a nu E can transform into an electron and vice versa in a weak interaction. And similarly, a muon into a muon neutrino and vice versa. And similarly here. That's why they're grouped the way they are. Neutrinos then, each neutrino is closely related with its charged companion. But there's a big difference between neutrinos and the charged companion. First of all, the neutrinos have no electric charge. They're neutral. Second of all, the mass of neutrinos is much, much less than the mass of the charged counterpart. The mass of any one of these neutrinos is less than a millionth of the mass of the electron. For a long time, in fact, people thought neutrinos might be massless, but now we know that's not the case. In any case, the mass is very small. In fact, the word neutrino means in Italian, little neutral one, and it was the name was given to it by the great Italian physicist Enrico Fermi. Little neutral one, it's a good name. Neutrinos don't have any electromagnetic interactions. They don't have any strong interactions. The only interaction they have among these three is the weak interaction. How weak? What does weak mean, anyway? I think the best way I can explain that is by giving an example. So let's think about our sun. Our sun emits a tremendous amount of energy, day in and day out, year in and year out, century in, century out, always radiating a huge amount of energy. Where does that energy come from? We know that it comes from nuclear reactions that are generated deep inside the sun, right near the center, where the temperature is extremely high. In this region of the sun, there is a very high density of free protons. And these protons are continually banging into one another. And there is a reaction, the first stage in a chain of reactions that generates the energy of the sun, which is a weak reaction. Two protons collide and form a nucleus called a deuteron, which is really a neutron and a proton in a bound state, plus a positron, which is just the antiparticle conjugate to the electron, and an electron neutrino. This is a weak reaction because it involves neutrinos. And let's give an idea of how weak it is. it's easy to see how weak it is by thinking in the following way, that the protons in the center of the sun collide with one another. A typical proton at the center of the sun collides about 10 million times a second with other protons. But it has to collide with the other protons for almost 10 billion years before this reaction takes place. Almost 10 billion years. And once this reaction takes place, of course, the two protons are converted into a deuteron. That deuteron collides with another proton, but by a strong interaction, to form a helium-3. It takes about 2 seconds for that deuteron to be gobbled up with this proton in a helium-3. So 10 billion years for a typical proton to produce this reaction. And once this deuteron has been produced, it's gobbled up with this proton to form a helium-3 in 2 seconds, typically. That gives you an idea of the difference between a weak interaction and a strong interaction. Also, once that neutrino is produced, it doesn't collide with anything in the sun because the sun is almost transparent to it. It escapes by flying out of the sun in a straight line with merely the velocity of light. So it only takes about 2 seconds to escape from the sun, in spite of the fact that the sun is a tremendously massive object, 300,000 times more massive than the Earth, and with a radius 100 times greater than the Earth. But the neutrino flies through the sun as if the sun were transparent, because it interacts so weakly. That neutrino may be headed in the direction of the Earth, and when it arrives near the Earth, it goes through the Earth also as if it were transparent, almost. It also goes through everything on the Earth, including you and me. How many neutrinos are going through us from the sun every second? We can calculate that fairly easily. It's 60 billion neutrinos per square centimeter per second going through us all the time. Just put your hand up so that the plane of your hand is perpendicular to the line of sight to the sun. Every second, 60 billion neutrinos per square centimeter going through your hand. But you don't feel it and you don't notice it. Why not? Because those neutrinos are not interacting with you because you're transparent with them. That's been happening for 5 billion years, ever since the sun formed, and it's going to happen for another 5 billion years until the sun comes to an end. Huge numbers of neutrinos. Now, the fact that a neutrino can go through a colossal amount of matter without interacting, like going through the sun, like going through the Earth, going through you and me, makes neutrinos very, very hard to detect in a physics experiment. Why? Because the only way a neutrino can be observed in a detector is if it interacts with the matter in the detector. But if the Earth is transparent to a neutrino, surely the detector will be transparent to a neutrino. Almost transparent. You can, if you make a detector massive enough, and if you're willing to tolerate low enough counting rates, observe a few neutrinos with a detector. Just give you an example. There is a neutrino solar neutrino detector in Canada, in Ontario in Canada, the Sudbury solar neutrino detector. It consists of 1,000 tons of heavy water, 1,000 tons. That's the kind of mass scale you need to make a workable detector for neutrinos. Now also, the counting rates are so low because of this weak interaction that you have to worry when you make such a detector. about background noise, background events. What kind of background events? Well, cosmic rays cause background events in a detector. So if you have to build your detector way underground, maybe a mile underground at the bottom of a deep mine, that's where all neutrino detectors are located in the world. Inside of a mountain or at the bottom of a mine. Makes life difficult. And when you put it at the bottom of a mine, you have to worry about the radioactivity from rocks. So it's a tough life doing neutrino experiments. It requires fortitude, requires patience, requires longevity. It's not easy. Nevertheless, people have done neutrino experiments, and especially in the last dozen or 15 years, there have been some very, very successful neutrino experiments. I've just mentioned solar neutrinos, and I mentioned that the sun generates a vast number of solar neutrinos. Are there other ways of producing neutrinos? Sure. Let me just mention a few of them. Mentioned solar neutrinos. Nuclear reactors can produce neutrinos. They do all the time. In a nuclear reactor, you have fissionable material. You have neutrons bombarding heavy elements like plutonium or uranium and causing the nuclei to split apart and form smaller nuclei. And generally speaking, those nuclei are unstable. They decay to stable nuclei. Here's a nucleus. We usually denote a nucleus schematically by writing Z and N. Z is the number of protons in the nucleus, the atomic number. N is the number of neutrons. And in a radioactive decay, Z and N will go to Z plus 1, N minus 1, because the neutron turns into a proton. And an electron is emitted, and an anti-electron neutrino is emitted, E bar. This is a typical nuclear beta decay. That's the kind of decay that occurs for an unstable nucleus in a reactor. And so you can see you produce anti-electron neutrinos, or electron antineutrinos. Nuclear reactors are very powerful sources of low-energy electron antineutrinos. Of course, when such an antineutrino is produced, it goes right through the walls of the reactor, right through the shielding, and can travel very large distances through the Earth. To give you an example, in Japan, as I'm sure you know, Japan has relied very heavily on nuclear reactors for electric power, at least until last year when they had their catastrophe with the tsunami. There are many, many reactors in Japan. There's a laboratory in Japan on the west side of the island of Honshu, the main island, which is buried deep inside of a mountain called the Kamioka Mountain. Surrounding that mountain, at distances of the order of 100 kilometers, are 53 nuclear power reactors. They're all generating, or they were all generating, very large numbers of electron antineutrinos. And that laboratory detected those neutrinos in a very, very important experiment that was just completed in the past year. They've been going on for about a decade. So nuclear reactors are used to generate neutrinos. There's still another way to generate neutrinos, still several other ways. High energy accelerators make neutrinos. high-energy accelerators usually accelerate protons to very high energies. Those protons can be used to produce pi mesons, which decay, produce neutrinos, and you can make a beam of neutrinos. Usually there are muon neutrinos and antineutrinos. The energies of such neutrinos are about 1,000 times greater than the energy of solar or reactor neutrinos. Then there's still another way. Cosmic ray neutrinos or atmospheric neutrinos, same thing. Top of the Earth's atmosphere, neutrinos are generated in the following way. You know, perhaps you've heard about cosmic rays. What is a cosmic ray? Cosmic rays are very high energy particles that are generated at vast distances from the Earth, deep in the universe. Mostly they're protons. They come in and strike the nuclei at the top of the Earth's atmosphere. Most of the nuclei at the top of the Earth's atmosphere are nitrogen and oxygen because, as you know, nitrogen and oxygen are the most abundant atoms in the atmosphere. When they do, they produce large numbers of pions. The pions decay to muons and neutrinos. The muons decay to electrons and more neutrinos. So you end up producing large numbers of muon neutrinos and electron neutrinos. The energies of such atmospheric neutrinos are approximately the same as the energies that can be produced in a high-energy accelerator, maybe 1,000 times greater than for solar reactors. Those neutrinos have also been detected in neutrino detectors deep underground. And finally, there's another source of neutrinos. This is the most bizarre of all. Perhaps you know that our universe began about 13 billion years ago with a gigantic explosion. It was called the Big Bang. In the Big Bang, vast numbers of neutrinos were produced. They had, at that time, energies about the same as the solar neutrinos. But those energies have degraded a great deal because the universe has expanded. And so those so-called relic neutrinos, relic from the Big Bang, are now of extremely low energy. It's fairly easy to estimate how many there are. One can estimate that in every cubic centimeter of space, there are several hundred such neutrinos. Inside you, inside me, in this room, everywhere, there are several hundred neutrinos per cubic centimeter that are left over from the Big Bang. It's too bad we can't detect them, but nobody knows how. It would be very interesting if we could. Now I want to talk to you about some experiments that have been done since 1998, which involve solar neutrinos, reactor neutrinos, accelerator neutrinos, and atmospheric neutrinos, which have discovered an amazingly interesting phenomenon. That phenomenon is called neutrino oscillations. I'll try to explain it in as simple a way as I can. Neutrino oscillations. These experiments were first done in 1998 and they're still continuing. And they produced an effect which is extremely interesting and revolutionary. Well, it's interesting if you're interested in it. Try to explain it in this simple way. Suppose we form a neutrino. For example, in this reaction, we can form an electron neutrino. Suppose we do. At some point in space and at a certain time, the neutrinos form. And suppose it flies off in this direction. Of course, it's moving with a very high velocity, essentially the velocity of light. So if we look at this trajectory, we can say that when it reaches a certain point, time has elapsed since it was formed. And here we ask the following very simple question. Is that neutrino, which we might observe here, if it started out as a neutrino nu E here, is it still a nu E here? Or is it perhaps something else? The answer is it is not simply a nu E at a later time. In fact, what happens is that this neutrino gradually and continuously transforms itself from a nu E into a mixture of nu E, nu, and nu tau. It's as if the neutrino were a chameleon which can change its color continuously. How does it do this? Well, nobody knows how it does it, but we can describe that it does happen, and we can determine the parameters of this transformation. What happens is that if you were to observe this neutrino here, you would find that the probability that it's an electron neutrino is less than unity, and the probability that it's a muon neutrino or a tau neutrino is greater than 0. Moreover, this process is cyclic. If we go to a certain point, what we might find is that the probability for it to be an electron neutrino, which started out to be 1 here, has dropped down to a minimum at this point. And then it starts increasing again. And then if we get to a point, let's say this is after a half cycle, and we get to a full cycle, either in distance or in time, it's an electron neutrino again. And then the cycle repeats itself. So if we were to plot the probability as a function of time, what we would see is that the probability that it's an electron neutrino starts out at 1, goes down to some minimum value, comes back up, and then reaches 1 again, and then goes back down again and comes back up, and so forth. You can see that this is a periodic or oscillatory phenomenon. And so it's called neutrino oscillations. Now, this is a fantastic thing. Fantastic for several reasons. One, it's extremely hard to observe, but people found ways to observe it. Second, it was anticipated by some very clever people, theoretically, before it was ever discovered. Those are two interesting things about it. And now, it has some very important implications that I won't go into, but I'll mention just one thing, and then I'll be finished with my discussion about neutrinos. Not only is it interesting in its own right, but it also has been, we've been able, by using this phenomenon of neutrino oscillations, to solve a long-standing problem in astrophysics, a problem called the solar neutrino problem. I think I'll try to explain this one also as simply as I can. The solar neutrino problem. What is the problem? Well, you know that there's a branch of theoretical astrophysics which is concerned with the structure and evolution of the stars. How does it work? Well, you'd have to start with the empirical data that has been developed for many, many years by many astronomers concerning the properties of stars, the mass, the luminosity, the age of the star, if possible, the radius of the star, the composition of the star and other details. Then you take all that data and you take the basic laws of physics which pertain to the star, and you build a mathematical model in the form of equations. And you try to solve these equations. Usually they're so complicated that you need to use computers, but that's fine. The solution to these equations gives you a picture of how the star, the structure of the star, and how it evolves in time. That's called the theory of stellar evolution. It's a well-established and successful branch of theoretical astrophysics. It's been applied in greatest detail, not surprisingly, to the sun, because the sun is the star that we know most about. That model makes predictions about the sun. It predicts, for example, what the flux of neutrinos will be from the core of the sun. Now, no mathematical model of a physical system is worth anything if you can't test it with observations. But you can't test a theoretical model of the star very well simply by looking with optical observations of the star. Because optical observations only enable you to look at the surface. Really what you want to do is know something about the interior. The only way to know about the interior of a star, the deep interior, is to observe the neutrinos because they come from the interior. The light only comes from the surface. So, in the late 1960s, the first solar neutrino experiments were done to measure the flux of neutrinos from the sun. And it was attempted to compare that to these theoretical calculations. And what was found? What was found was that the observations told us that the flux of neutrinos was just about 1/3 of what the theoretical model predicted. Those early observations were followed with some other observations, and that discrepancy persisted, that factor of 3 between the theory and the observations. That discrepancy is the solar neutrino problem. Now, that discrepancy has been solved, has been rectified just in the last 10 years. How? With the advent of neutrino oscillations. And the explanation is extremely simple. Certainly, in the sun, the neutrino is born as an electron neutrino. But as it travels between the sun and the earth, it becomes a mixture of electron neutrino, muon neutrino, and tau neutrino. If you consider all the neutrinos from the sun, which have an energy distribution, and which come from different parts of the sun, then this mixture becomes somewhat incoherent. And the net result is that what you have in effect is an average of each one of these with equal statistical weights. In other words, 1/3 probability to be electron neutrino, 1/3 probability to be muon, 1/3 to be tau. If your laboratory detector is only sensitive to electron neutrinos, it will detect only 1/3 of the flux, because the other 2/3 is in these two categories. Finally, that was the realization. So what you have to do is make a detector that's sensitive to all 3 varieties. And when that was done, in this Canadian detector that I mentioned, agreement was achieved between the observations and the stellar model. As simple as that. What's the upshot of all this? It's simply that with the aid of understanding of neutrino oscillations and with these beautiful experiments done deep underground, one can verify that these theories of stellar structure and evolution are on the right track, that they're valid. the explanation of how the sun works is really a valid explanation. So we see that these neutrino oscillations have solved the solar neutrino problem. Okay, I think I'll stop here, and I'll ask if you have any questions about neutrinos or anything else. Yeah?
What about the recent discovery of neutrinos going faster than light?
Ah, yes, I can explain that. These were neutrinos that were generated in the high-energy accelerator, the Large Hadron Collider in Geneva, the new accelerator, and detected several hundred kilometers away in a laboratory in Italy. And it was claimed that these neutrinos traveled slightly faster than the speed of light, which contradicts a fundamental principle from special relativity. This made sensational headlines a few months ago in the newspapers. A lot of physicists were very skeptical about it, including me. And it turns out the experiment was wrong. There was a loose cable in that experiment. It was not connected properly. That's all. When that cable was connected, the effect went away. People were quite embarrassed. Do you have any other questions? Yes.
When in the oscillations, the electron neutrinos turn into the other kind, it has equal probability to turn into any of the three kinds?
No, it's a little more complicated than that. The probabilities are not quite the same. If we had only two neutrinos, the mathematical analysis of the oscillation would be quite simple. But when you have three types, the coupling between this one and this one might not be quite the same as between this one and this one. I don't know whether you've ever done any experiments in mechanics in a laboratory in physics or not, but an analogy to this would be several pendula coupled together with springs which with different restoring forces, and so you have several different periods of oscillation and several different couplings, and so the normal modes are kind of complicated. But one thing I can say that it really isn't specific to an electron neutrino. If we started out with a muon neutrino, it would oscillate into the other varieties. Or if we started out with a tau neutrino or the antineutrinos, all of them would exhibit this neutrino oscillation, but the details would be slightly different. Yeah?
You said before that neutrinos are produced when things decay?
Yes.
Do neutrinos ever decay?
No, not to our knowledge. No. They're stable. Like the electron is stable. The electron is stable, but the muon is not. It decays to an electron and two neutrinos. The tau lepton can decay similarly, although its decay modes are a little bit more complicated. So the muon has a lifetime of only about 1 millionth of a second. And the tau has a lifetime of 10 to the minus 13 seconds. Aside from that, the muon and the tau are very similar to the electron. Yes?
So they first thought it might not have mass, but now we think it has a very small amount of mass. How did they get from the first to the second part of that?
Well, neutrino oscillations could not happen unless neutrinos had mass. And in fact, it's a little more complicated than that. If you take a neutrino which has a definite weak interaction quantum number, if it belongs to a definite generation like nu-e, then it cannot have a definite mass. It must be a mixture of neutrino states with different masses. And similarly, for each one of these, this is really bizarre, but I can give you an analogy. If you have linearly polarized light, it must be a superposition of right and left circularly polarized light. if you have right circularly polarized light, it must be a superposition of two different linear polarizations with different phases. You can't have both linearly polarized light and circularly polarized light. Similarly, if a neutrino is in a definite weak interaction state, it cannot have a definite mass. If it's in a definite mass state, it cannot be a definite weak interaction state. It's analogous to the polarization. So the fact that we have neutrino oscillations means that these states, UE, mu, and nu tau, although they're definite weak interaction states, they don't have a definite energy because they don't have a definite mass. Energy and mass are related in relativity. That's the reason we have the oscillations. It's a subtle, tricky business. Now you might ask, why is all this happening? Nobody knows the answer. I wish we knew the answer. It's something very deep. And eventually, maybe somebody will explain why it happens. Right now, it's a mystery.
Since neutrinos travel through space, and basically the sun, for example, is invisible to these things, is it possible that it's traveling in a slightly different dimension or something, or no?
I don't know about that. That's just, people speculate about higher dimensions. The only thing that we can really say from our experiments is that the probability of a neutrino interacting with anything is extremely small. The coupling is extremely weak. That's all. That's about all we can say.
What do we know about anti-neutrinos?
Anti-neutrinos, we know essentially as much about anti-neutrinos as we do about neutrinos, because the reactors produce anti-neutrinos, the sun produces neutrinos, high-energy accelerators can produce both, and the atmospheric neutrinos are of both types. So essentially, we know as much about anti-neutrinos as neutrinos. But there's one other thing. You know, the particle that's conjugate to the electron, the antiparticle conjugate to the electron, is a positron. It has an opposite charge. The particle conjugate to the proton is the antiproton. It has an opposite charge. But what about neutral particles? A neutrino is neutral. It has no charge. So is an antineutrino different from a neutrino, or is it the same? There's a big question about that. It's a question which has not yet been answered. If it's described in one way, it's different. We can call a neutrino a Dirac neutrino. That Dirac was a great physicist, great theorist, and if there's a certain description of neutrinos, if he was right, neutrino and antineutrino are distinct. But there was an Italian physicist who made a different description, Ettore Majorana, a very mysterious character, by the way. There's a story about him. I'll tell you in just a minute. Majorana proposed that the neutrino and the antineutrino are identical. Nobody has been able to determine whether Dirac was right or Majorana was right. There are experiments which can determine it, but they haven't been done yet. Incidentally, what about Ettore Majorana? He was a brilliant guy, a child prodigy, a person of exceptional mathematical talent, like the gentleman you were telling me about. He also was a bit peculiar psychologically, a recluse. Enrico Fermi said he was the most brilliant person that Fermi had ever met. He was including Einstein, Bohr, Pauli, Dirac, and Schrödinger when he said that. Majorana was a recluse who took a boat trip from Palermo, where he was from, in Sicily, to Naples. and his friends went to meet him at Naples. The boat arrived, Majorana was not on it. He must have jumped off and disappeared into the ocean. This was in 1938. People have said he disappeared. Maybe he's appeared someplace else. Some people have suggested he ended up being a mafia don in Brooklyn. But I don't think so. I think he drowned. I think he drowned in 1938. He left a legacy of some unpublished papers that people have dredged up that are truly remarkable. And he was extremely young when he died. A phenomenon, a rare person.
How do you spell the last name?
I'll write it for you. Hettore, that's Italian for Hector. Majorana, M-A-J-O-R-A-N-A. Died at age 28, I think. Fairman was not given to exaggerations, and when he said that, it was something special.